In this video, I want to talk about holes and hole notes. So in the past, we've mostly made holes in parts using a circle and then extruding a cylinder out of that part. But in general, making an actual hole is better because we have more options to easily make certain types of holes which are common in engineering. And also when we document those holes, a lot of information is contained in the hole when we make it as a hole rather than an extruded circle. So let's talk about these. For some definitions, we can have a lot of holes. So a through hole is a hole that cuts through the entire thickness of an object. And in this particular part here, I've got a through hole. Here it just is a hole, and it'll look like this when you document it. There's a clearance hole. This is a hole large enough to allow a screw head and a driver to pass through. And there's a blind hole. This is a hole that does not cut all the way through. For example, these on the left and right are blind holes. So we have our through holes here. This could be a clearance hole. And these are blind holes. Here are some other ones. We have a countersink hole. That is where you have a conical shape recess around the hole at the surface, and it's often used to accept a tapered screw so that the screw head is recessed below the surface of the material. Counterbore is similar to the countersink, but instead of a conical shape, we have a cylindrical shape, as shown here. So it's a cylindrical recess around the hole at the surface, often used to receive a bolt head or a nut. Again, so it's recessed below the surface. And finally, we have a tapped hole, in which we put threads on the interior of the hole. Here are some symbols. I think we've used some of these before. Here's the diameter symbol. This is the symbol for a counterbore, countersink, and this indicates the depth of a hole. So hole notes was just circled here. And this is the information that is automatically included inside a hole. So when we dimension a hole, we get all this information, which we don't get if we dimension a cylindrically created thing using extrude. So this is a 1/4 inch diameter blind hole drilled to a depth of 0.75. So this tells us it's a 1/4 inch diameter, the depth, and then the 0.75 tells us it's a blind hole. It doesn't go all the way through. This symbol here tells us it's a counterbore, and then the diameter of that larger counterbore area is 0.38, and it goes down a 1/4 inch. This is a 0.38 inch diameter blind hole, and it's drilled 0.50 inches deep. So this is the depth symbol, 0.5, so it's 0.5 deep. This is the through hole, so that's 0.38 inch in diameter. And finally, we have a countersink hole shown here. And the shaft, or the hole itself, is 0.5 inches, and we're told it goes all the way through, and indeed we can see the tan area in the back, so it suggests it goes through. And then the conical region around it is given after the little cone symbol, and it has a diameter of 1.0, and it's at 82 degrees. So threads are dimensioned with the use of local notes. So two methods are Unified National Thread Method and ISO. So Unified National Threads, we have the major diameter of the hole, the threads per inch, and UNC with the C being coarse. There will be an F there if it's fine, coarse or fine threads. We're going to skip ISO thread notes, and we're going to end that presentation there. We're going to quickly move over to another one concerning alternate views. In some cases, orthogonal projections like front, right, and top, and pictorials are not sufficient to specify all the details of the part. So there are 3 additional views that we can create in our drawings in Inventor. There's a section view, auxiliary view, and a detail view. Here we're going to focus on the section view, and I will mention the detail view as well. So the detail view should be highlighted. So recall that we made a windshield, and here it is on the right here. So let's see what it says here on the bullets. So the section view provides a view of an object as if it were cut by a saw. Location is indicated by a cutting plane line on another view. For example, this appears like it could be the bottom view of our Automobilex windshield, and this symbol here is called defines the cutting plane. So we've cut it right through there in a direction that's out of the paper into the paper. And let's see what that looks like. So the cutting plane line, it indicates the location of the cut. It's thick and broken, so dash dot, dash dot, dash dot. Arrows indicate the direction of view, so in this particular case, it's as if I'm up here near the top and my eyeball is looking straight down. And so what I'm going to see is the stuff on the other side of the cutting line, but the cross-section. And it's labeled with a letter for identification on a drawing. So if you have several of these, you would label them A, B, and C. Section lines. They're hatch lines that indicate material that was cut at the cutting plane line. So these are quite narrow, but in parts with larger areas cut out, these will form a large fraction of your view. But it's just the little diagonal line there, the hatch, as it's called. So these are the section lines, and again the cutting plane line. We are going to only focus on the full section, and that's where the cutting plane line passes fully through the part. That's what we've seen already before. And the part of the object behind the cutting plane is removed away from the direction of the arrows. Well, let's see what that looks like. So here we have an object that's not very, it's got a view right here which is not very illuminating. So we're going to take a cross section through it, and so the cutting line AA, and so we take a saw and we cut it through there, and that half of the part is removed, so it's gone. And we look in that direction, and what do we see? We see that. And so the section lines indicate that this is the material that's sort of inside the part that we wouldn't normally see. And so that is a full section example. So you can imagine how useful this might be when dealing with things like cylindrical objects and many others as well. Okay, we're going to skip these next views, and we're going to move on to a detail view. So this is an enlargement of a portion of another view to illustrate small features on a part. So what do we mean by that? Well, here's an example. Say we've got this is called a rack gear, R-A-C-K, and we've got a front view here, we've got a right view here, top view, isometric. You can see that if you wanted to get down and dimension these teeth here, you're going to have a hard time with this view. But if you blow this thing up, you're going to run out of paper, and then everything gets big. So what you do is you use a detail view, and you can just take a little circle and move it over here. And this time it's been scaled up by 2 to 1. Could go higher if you like. And therefore we have a little more room to specify that the angle here is 40 degrees. The pitch of the teeth is 0.26 inches from here to here, and the height are 0.18. So this is a detail view. So section views and detail views and making holes and hole notes are the contents of this video. So if anything's sketchy, go back and watch it again. Thanks for watching.